In this problem, we are given f that's defined on this interval 0, 1, and it's going into R. It's also continuous. We also defined the term an by 1 over n, the integral between 0 and 1 of t to the power n f of t dt. So we want to prove that the series having the general term an is convergent. The problem is we don't know the expression of f of t. Also, we don't know if this an is positive or negative. Okay, because most of the time we are applying the tests for convergence to only positive terms. We can deal with the other ones later, but if we can deal with the positive one, that's fine. We can deal with all the others. The issue with that is that our function here is defined on this interval 0, 1. Okay, so f can be like this, can be like this. It's continuous. Okay, so here it can be positive or negative. So the idea is that when f is defined on some bounded interval, it's bounded by itself. So that means f of t is less than a certain number m for all the t's in this interval 0, 1. Okay, so that's what we're going to use. Also, since we don't know if this an is positive or negative, we're going to take the absolute value of it. So basically we're going to use this one. In fact, we're going to prove that if the series is absolutely convergent, then our series is convergent, because we know that if a series is absolutely convergent, then it's convergent. The series is convergent. This is more powerful than the regular convergence. So what we're gonna do is we're gonna try to find some value for an, okay, and use the comparison test to prove that this series is convergent. Okay, so that's what we need to do. So saying that, let's assume that f of t in absolute value is less than a certain m for all the t's in this interval 0, 1. Okay, that means f is bounded by a certain m because it's continuous, and this interval here is bounded. So this is a closed interval. So that's why we have this result here. Okay, so this is the extreme value theorem in somehow. So we can't escape this interval. We always stay here. So let's find the absolute value of an. So here we have that the absolute value of an is the same as that of this value of the integral. So 1 over n, the integral of t to the power n f of t dt between 0 and 1. Now we're going to use the fact that this one is less than 1 over n, because this is positive, 0.1 t to the power n f of t in absolute value dt. Okay, so here we get this is less than 1 over n 0 to 0, 1 tn. It's positive, and I'm assuming. Okay, so t to the power n is positive because between 0 and 1, and the absolute value of f of t is less than m. So we have m dt. I'll take m outside. It's going to be m over n, and I integrate t n dt. So that gives me m over n plus 1. So my an is less than this. Okay, so now I can use the comparison test here now. So this is my, think of this one as my an in general that you have in this is my an, this is my bn. Okay, so assume that for all n, I have this result for all n. So this an is less than bn, which is m over n times n plus 1. But this one is convergent. Okay, so this series here, this series m over n times n plus 1 is convergent by the B series test, because here you can write this one as sum m over n squared, and 2 is bigger than 1, than p. Okay, remember that, and we can take the m outside because this series is convergent when alpha is bigger than 1. So here this is the same thing. Okay, so this is the same. If you don't like it, you can use the integral test for series and prove that the series 1 over n times n plus 1 is convergent. Okay, there are many ways, but anyways, so this one, so an in absolute value is less than this quantity m over n times n plus 1, and this for all n, and this is convergent. Okay, this series is convergent, therefore this series is convergent. Okay, and by the comparison test we conclude that the series an is less than an, which is convergent. And also we know that an absolutely convergent series gives us that the regular series are convergent. Okay, so absolute convergence gives us regular convergence. So if it's absolutely convergent, then the series is convergent. Therefore this one is convergent. Okay, therefore our series that have this term, so our series, which we can write as 1 over n between 0 and 1 t to the power n f of t dt as n goes from 1 to infinity, is convergent. Okay, so we have many ideas here, but the key idea is that if you have absolute convergence, then you have the convergence. Okay, it's more powerful than the regular convergence. And also the comparison test is very useful to prove this result, along with any other tests. Okay, this shows our result that if we are given a function that's defined on this interval 0, 1, continuous, and if we define the general terms of the sequence an by 1 over n, the integral between 0 and 1 of t to the power n f of t dt, then this series is convergent. Okay, since we have absolute convergence, this series is convergent, and this is what we needed to prove.